level curves. Because this class is multivariable calculus, we will start to talk about multivariable functions. So these are functions which has more than one input. So this function depends on x and y. And suppose that you have this as your output. So that if you have f of 1, 2, what's that? That means 1 goes into x, and then 2 goes into y, which gives you this number. Now, if you recall, when you had f of x equals to x, the way we drew this was by replacing fx by y, and we drew the graph of y equals to x, and that's how we got this graph for the graph of the function, right? In the same way, we have to replace this by some variable, but we can't use y because that y is already used. So what variable should I be using? Yeah, f of xy is z equals to x squared plus y squared. Okay, so this is going to be a graph of xy, and now you see that it has 3 variables, x, y, and z. So in order to draw this, we need a 3D coordinate system. Okay. Whenever you open a Google map, there's somewhere in the Google map that you can click that's called terrain map. If you click the terrain map, you might see something like this. Okay, what does that supposed to mean?
Elevation.
Yeah, each line is the line of same elevation. They have the same elevation. So if this was like elevation 1, 2, 3, 4, then it's somewhat of a hill, right? Yeah. This is a higher point. Okay. If it was like negatives, that means it's a valley. So it's something going in, right? So if you want to know what the shape of this graph is, there's one strategy, which is to make level curves like this one. See, you were thinking of z as the elevation. So here, because these are both squared and added, you can't have z as negative. So you can think of the various values of z. So let me state that here. The definition the set or collection of 2D curves one obtains by setting z equals to k or some k values. Usually like plus minus 1 or 0 plus. So e.g. 0 plus minus 1 plus minus 2 and so on and so on. Is called level curves of fx1. Okay. So let's try that. We did something similar last time, so it won't be so hard. So as I said, k equals to 0 is the lowest, right? We're replacing z by some k. So we're trying to draw k equals to x squared plus y squared. And k equals to 0 is the smallest k you can have because these are both squared. Now, this is a circle of radius 0, which means it's a single dot in the middle. Okay. Okay, what if I put 1? What does that give us? Circle of radius 1. Right? And then what if I put 2 equals to x squared plus y squared?
Radius 2.
No, not radius 2. It'll be radius
Rad 2.
rad 2, right? It's rad 2. Because 2 is equal to square root of 2 squared. And the formula for the circle is x squared plus y squared equal to r squared, right? So you need to do that, okay? And then you have square root of 3, square root of 4, and which is 2. So if you collect them, this is what we're going to get. So let's say this is 1, and then let's say this is 2. But that really corresponds to k equals to 4, right? Because 4 is 2 squared. And then there are 2 numbers in between, so slightly before. The square root of 2 is about 1.4. Square root of 3 is about 1.7. So you have 1 dot here, 1 dot there. That's square root of 2, square root of 3. So you have this, and then the next one will be smaller. I made this too. Yes. This is it's much more close to 4. So it's like 1, 2, 3, and then 4, and then 5. Okay. So now we see that if you had a graph of x squared plus y squared, z equals x squared plus y squared, then every level curve is going to be a circle. And as you increase, the circles grow outward. Right? So you have this point, and you have a circle that's growing. But it doesn't grow, the radius doesn't grow at a constant rate. It kind of slows down, right? So it's like this. Is that good? Does that make sense? Okay. So what kind of shape is that? So sometimes it's not so clear just by looking at the level curves. So what you should do is you should add in the xy trace or yz trace or something. Okay? So if you have z equals to x squared plus y squared, the xz trace is the intersection of this graph with the xz plane. Now every point, so if here's x, here's y, and here's z, xz plane will be right here. And every point on this xz plane will have y coordinate 0, right? So therefore, to get the intersection between this curve and the xz plane means you're setting y as 0. So let's see what that does. That gives you z equals to x squared. Oh, I know this graph. What is x squared? Parabola, right? So if you drew this, it's going to be here's x, here's z, and you're going to get this. And if you also do xy trace, no, z, yz trace, that means you're setting z equals to 0. And again, no, you're setting x is 0. X is 0, then again, you set x is 0 and you get z equals to y squared, right? So here is y, here is z, here's like that. Same thing. It's the same exact graph. Both are x squared, y squared, same thing. Now, the xy trace sets z as 0, but that's same as the level curve as 0. So that's nothing new. So I'm not going to draw that. What this is saying is that if this is x, that's y. These are x and y. What's z? Z is coming like that, right? And then if you took this surface, which is something like a funnel, and you cut it like that, which is the xz plane, it's going to give you a parabola that way. And if you cut it like this with the yz plane, see, this is the yz plane because z is coming out of the board, okay? And there's y, so this plane is yz, and you really have to think about the actual surface being something like this, right? And if you cut it, then the intersection is what we got over here, which is a parabola. And putting all those together will give you a pretty good idea of what the picture should be for the actual surface. So if you were to draw z equals x squared plus y squared, that's going to be, here's x, here's y, here's z, and it'll be a bowl-shaped thing with circular, it'll have circular cross sections. Okay? So that's the graph of z equals x squared plus y squared. Say this is known as paraboloid. Usually if you get an object by rotating one around the other, that's you name it as oid. Okay. So let me change this slightly. What if I put 2 here? So this is example 2. Well, still 0 equals to 2x squared plus y squared gives you just a single point. The only pair of numbers that satisfy this is 0, 0, right? Anything else you put in, that will be bigger than 0. So the only solution to this is 0, 0. So at the level curve k equals to 0, it'll still give you a point at the center. Well, what if you put 1 for the k value? What does that give you? Well, think of this as x over square root of 2, x over 1 over square root of 2 squared plus y squared equals to 1. And we talked about the conic sections before, and this is how it works. Dividing by a number will expand the graph by that amount. It will like stretch or shrink. It will either stretch or shrink the graph by that amount. So for example, if you put 2 and 3 there, then this will be taking the unit circle of size 1, stretching twice in the x direction, and this will be stretching 3 times in the y direction. So you get this ellipse, right? So that's what happens in general. So I'm just pointing out what this formula does. And the reason I rewrote 2 times x squared in this complicated way is so that I can pick up what a is and what b is. B is just 1. We didn't divide by anything. But what is this doing? We made it smaller, right? So this is about 0.7. So it went from 1 to 0.7. Okay. So in other words, the y coordinates stay the same. So here's the unit circle. The y coordinates stay the same, but the x coordinate shrunk to about 70% of its original length. So this is what you get. Okay. And this is going to be your level curve at k equals to 1. It'll be k equals 1 level curve. Now, if you continue on and increase this to 2, you're still like increasing the radius, right? But because of these ratios staying the same, it will still have the same kind of ellipticity. Ellipticity of a circle is defined as the length of the largest radius divided by the length of the shortest radius. Okay. That ratio will always be square root of 2. So this side will be square root of 2 times the other side. Okay. So that's what you get. And what does that mean? What will be the graph of z equals to 2x squared plus y squared? How is that different from that one? It's like taking this and squashing it in the x direction, right? So it'll be like something like this. Fix that. So here's the x direction, here's the y direction, and that's the z direction, up in the z direction. And it's compared to this is like in the x direction, we're squashing it, okay? So that the cross sections are not circles, but ellipses, okay? So in such a case, we say this is elliptic paraboloid. Elliptic paraboloid. Okay, now in the next example, I went from plus to minus. This time something changes. This time you can have k value to be negative because if you subtract two things, if y is bigger than x, of course they can be negative, right? So we're going to have to first start with k equals to 0. If I say k equals to 0, yeah, I don't think many of you have seen this graph before. This one you just have to have seen it once. It's hard to figure this out if you never have seen the graph before. So what you do is you rewrite this as, because this is difference of two squares, it factors as x minus y times x plus y, right? And if two things multiply to 0, either x minus y is 0, which gives you x equals to y, or x plus y is 0, which gives you y equals to negative x. So that gives you one graph, which is y equals to x, and the other graph is y equals to negative x. Okay? In other words, this single equation gives you two lines. Have you ever seen that? Like having a single equation actually giving you two lines? Okay. Now, what if I do k equals to 1? K equals to 1 case will be setting 1 equals to x squared minus y squared. Well, this one, if you set y as 0, you get x squared as 1, right? So setting y as 0, you get x squared equals to 1. Therefore, x is plus minus 1. What's that? You have 1 comma 0 and negative 1 comma 0. Right? Okay. But then, if you move y squared over here and move the 1 on the other side, and you get y squared equals to x squared minus 1, and think about this as plus minus square root of x squared minus 1, definitely the domain is x should be greater than 1 or less than negative 1. If x is between negative 1 and 1, this will be negative and you don't get any graph. So you don't get anything for values between negative 1 and 1, okay? But once you have x greater than 1, this starts to increase, right? The value of y goes up. But when x is really, really large, then this negative 1 is not much of a concern. So the graph gets closer and closer to y equals to x. So y equals to x is what's known as the asymptote, okay? As it gets closer and closer. On the other hand, if you have, so that's for the plus. So this is two things. One is y equals square root of x squared plus minus 1, and y equals the negative square root of x squared minus 1. The negative of this will be just flipping this graph upside down, right? And that one will have the asymptote y equals to negative x. So it's going to be like this. Okay. But then this is symmetric with respect to the y-axis because if you replace x by negative x squared is same as x squared, right? So the graph on the left side is same as the right side, which gives you another one. Like that. And we have a name for such a curve. Do you know what it is? Hyperbola. Hyperbola. Yes, thank you. So this gives you a hyperbola. This, again, this means that the graph has level curves which are hyperbolas. Hyperbolas. So let's see what happens if I increase by 2. Well, it's very similar to how circles go. The moment you increase 2, that allows these values to be bigger than before, right? So you end up with a curve that's bigger. So you get another hyperbola, but this time, if you plug in 0 for y, you get the solution of 2 equals x squared will have square root of 2 and negative square root of 2 as the two solutions, right? So you get another one like this. Still, the asymptotes are y equals to x and y equals to negative x. In addition to this, if you take z equals to x squared minus y squared and take the xz trace, that still gives you z equals x squared because that means y is set to 0. And then, but then if you do yz trace, you get something different. That means you're setting x at 0. And if you take this equation and put x at 0, you get z equals to negative y squared. Okay. So that's interesting. That means here's x, here's y, and here's z. In the x direction, you have a curve you have a parabola going up, like that. Okay. And in the y direction, you have a parabola that's going down like this. Okay? And then every level curve that you get, the level curves are going to look like that. Just like that. Now, what if I do the negative? I said we need to do the negative too, and I forgot to do the negative. Let's try to do the negative. What happens if I do k equals to negative 1? Let's see what the x-intercept is. If you set y as 0, what do you get for x-intercept? If you set y as 0, what do you get for the x-intercepts? Say the obvious thing. What do you get?
X squared equals negative 1.
Which means I or plus minus I, but that doesn't exist on the coordinate system, meaning this thing is not going to have any x-intercepts. Okay? That one doesn't have any x-intercepts. However, it's going to have y-intercepts. How do you get y-intercepts? You set x at 0, right? If you set x at 0, what do you get for the y-intercepts?
Plus minus one.
Plus minus 1, right? That's what you get. So you're going to have plus 1 and negative 1, so the curve is going to pass through these 2 points, right? And furthermore, you can't solve this for y, rather you're going to solve this for x. You can solve this for x as plus or minus square root of y squared minus 1. So it's like that graph, but instead of going this way, it goes this way. Okay? Yeah. So it's like that. Yeah. And it still has the asymptotes. It gets closer and closer. That's what. Which means in this picture for the level curves, as you go under, the level curves go like that. Looks like that. Okay? All right, so that's still challenging to imagine, but we do have a nice shape that mimics this, which is Pringles. You know, Pringles potato chip. So how does that look? It's like that, right? Yeah. That's what this shape is. Okay. Another way to say it is it's a saddle. Yeah, if you know what a saddle looks like, that's this shape, right? So this will be like the horse's head. This will be horse behind, and then your leg goes over here, right? The saddle. And in fact, saddle is one of the official names for this curve, this surface. Okay, so this surface is called saddle, but the more technical way to say it would be to call this hyperbolic. Now we're going to eventually look at some other hyperboloids as well. So this is going to be actually, sorry, this is not hyperboloid. It's called hyperbolic paraboloid. Hyperboloid is for something else, and I'm going to show you it later. Okay? It's called hyperbolic paraboloid because you have cross sections that give you, if you cut it like this or that, you get parabolas, right? On the other side, it's if you cut it like that, you get hyperbola. So that's called hyperbolic paraboloid. Right? So we learned 3 types of paraboloid, right? The regular paraboloid, the elliptic paraboloid, and hyperbolic paraboloid. The usual paraboloid, where the cross sections are circles, are a special case of the elliptic paraboloid, and this looks completely different. Later on, we're going to look at this special point right at the middle because that's the place where it's like the we're going to talk about tangent planes rather than tangent lines. And this is a place where the tangent plane is horizontal. And any place where the tangent plane is horizontal is called a critical point. But this is somewhat special because it's neither maximum nor minimum. If it's like going this way, it's a minimum, but if you go this way, it's the maximum. So it's like a maximum in one direction, but minimum in the other direction. And such a point is called a saddle point. Okay. So that's going to come later. Right? Just like how in 2D, curves like this is not a graph of a function. In 3D, we have examples where z is not a function of x and y. So here's a case where this means x comma y comma z's norm squared is 1, right? That's what this means. But what does that mean? That means you're collecting all the points from the center that's distance 1 away from the center. If you collect all the points that's distance 1 away from the center in 3D, what object are you going to get? Collect every point that's distance 1 away from the origin.
Cube. Sphere.
Sphere, not a cube. Cube have the edges being further than the other parts, right? Yeah. So it's a sphere. It's like a three-dimensional analog of the circle, right? So this is going to give you a sphere, and this sphere is not a graph of a function, so not a graph of z equals a single function, single function of two variables. And one way to say it is that it doesn't pass the vertical line test. Yeah. So there's a three-dimensional version of vertical line test. Yeah, but that's not the important point. Rather, I'm just trying to say that when it comes to graphs that are not of this form, z equals to some function of xy, then just having the level curves are not enough. You need to take traces in all directions. So for this one, actually, you don't really want to take level curves. It's if you didn't have this intuition, then one way to quickly find out the shape of the surface is just try to draw all the xy trace, yz trace, zx trace. So here's xy trace. What's xy trace? You set z at 0, so you get x squared plus y squared equals to 1. What's that?
Circle.
Circle of radius 1. Okay, how about yz trace? That means you're taking x at 0, right? So you get y squared plus z squared equals to 1. What's that? Another circle, right? And then what about xz trace? That's going to give you x squared plus z squared equals to 1. So another circle of radius 1. Now what that means is that you have a three-dimensional object where here's x, here's y, here's z. First, xy trace is you cut the surface this way, and you get a circle. Okay. And then yz trace means here's x, here's y, here's z. So yz trace is over here. You cut it like that, and you get a circle. Okay. And then you have xz trace. This is the x, that's z. So xz plane is here. You cut it this way, and you get a circle. What can it be? It must be a sphere, right? So that's how you can choose these three traces and put them together to give you a sphere. Okay. Which is, yeah, sorry, this is a terrible drawing. Let me try to do better. Here's x, here's y, here's z. Here's a circle, like that, and then like this. Okay? So that's the sphere that you get as the graph of this guy. And you can kind of see in general, if you want the sphere of radius r, if you have x over a squared plus y over b squared plus z over c squared equal to 1, you get, this is like taking the sphere and you have three directions to stretch, right? So here's x, here's y, here's z. And you're stretching in the x direction by a, in the y direction by b, and z direction by c, and then you get this thing that's like stretched in different amounts, so that the cross sections will be ellipses rather than circles. Okay. So that gives you something called an ellipsoid. This is an ellipsoid, and as a special case, when if A equals to B equals to C equals to R, that's what? That's x over r squared plus y over r squared plus z over r squared equals 1, and then you can multiply by r, so you get x squared plus y squared plus z squared equals to r squared. What does this do? That means you're taking a sphere and you're stretching in every direction by radius r. So for example, if r is 2, that means you're doubling every direction, x, y, and z. So what's the new shape you're going to get? You're going to get a sphere of a bigger size, right? Yeah. So that's why this is a sphere of radius r. Okay? All right. And this one's quite similar to the one that we did before, which is like um, x squared. We did z equals x squared minus y squared, right? But now you have z squared equals to x squared minus y squared. Um, well, this can be thought as x squared equals to y squared plus z squared. And this time you want to draw the graph with different values of x, because then you know that these are all circles, right? If you have two squares added up equals the value, that's the circle, right? So what you can do is we can take, so let me see. Let me put numbers here. I think this is example 4, and this is example 5. Okay. So for this one, I'm going to draw the graph with various values of x rather than z. And in such a case, we call that x trace. And that's like, here's x, y, and z. And here's the x direction axis. And you want to set x equals to 1. What's x equals to 1? It's a plane that's perpendicular to the x-axis crossing at 1, right? So you have x equals to 1, x equals to 2, x equals to 3. So in other words, when you say x trace, you're really taking level curves, not going up, but rather going in the x direction. That's what you're doing. And the reason you want to do this is because if you take x as 0, you get 0 equals to y squared plus z squared. That's a simple point, right? And if you set x equals to 1, you get 1 squared equals to y squared plus z squared, which is a circle of radius 1. And then x equals to 2, 2 squared equals to y squared plus z squared. Okay, let me ask this question. What's the radius of this circle? 2, of course, right? 2 squared, so it's 2. So that means it's another circle, but twice bigger, okay? So if you look at the x trace, then you see that all the cross sections are circles. So here's x, y, and then z. In the x direction, if you take perpendicular slices, you get all of these circles that get bigger and bigger. These are the x traces. Now, because we have x squared, it doesn't matter if you plug in -1, you get the same thing. So you get another circles that's going up. And the radius is not slowing down. It's going at a constant rate because it's squared, right? So anytime you increase the x value, the radius grows at the same rate because radius is x. So you end up with something that looks like this. Now what is that?
Is it a cone now?
That's a cone, yeah. And then example 6, you can also do z squared equals to, say, x squared minus 2y squared. Now, anytime you multiply something that squashes it down, this time it's taking this one and you're squashing it in the y direction, right? So that the cross section will be ellipses. So this one will be like here, but the cross sections are ellipses. Here's the x direction, here's the y direction. And that has the name elliptic cone. All right, so sorry, I'm going a little bit fast because I have like less than 10 minutes. But here comes the last two of the types. Example 7. This one's pretty similar to the previous one, except you have z squared equals to x squared plus y squared minus 1, and there's another one with the plus 1, okay? All right. So example 7 is the one with minus 1. Let me write down example 8 as well. Z squared equals to x squared plus y squared plus 1. Now they look so similar, but the resulting graph has very distinct geometric feature. We'll see what it is once you graph it, okay? Okay, so let's start with example 7. You have, let's look at the level curves. So if you set z equals to 0, in other words, I'm looking at the z trace, then you get, or you can also say this is xy trace. This will be this, which is, yeah, all I did was replace z by 0. We're at example 7. And then just add 1 to the other side, and that gives you 1 equals to x squared plus y squared. What's that? Circle radius 1, right? Okay. What if I do z equals to 1? That's going to give you 1 equals to x squared plus y squared minus 1, so that's going to give you 2 equals to x squared plus y squared. What's that? Not radius to radius, square root of 2. Right. So if you put them together, once the smaller one will be here, if it says 1, the other one will be not double the size, but like 0.4 times, like 40% larger, not double the size. Okay, that's 2. So what seems to be happening is that in the middle you have a circle, but as you go, it does grow, right? It does grow. And this is true even if it was negative 1. So you can even say plus minus 1 because even if you plug in negative 1, it's squared anyways. Right? But then let's think about the xz trace. What's xz trace? You get z squared equals to y squared minus 1, right? No, x squared minus 1. X squared minus 1, because xz trace means set y as 0. And then, I think we've seen this before. So does this have a x-intercept? What's the x-intercept? To get the x-intercept, you'd set the other one 0, right? So if you set z at 0, you get x squared equals to 1. So you have 1 and negative 1. Right? I mean, one quick way to see it is, if you move this to the other side, you get z squared minus x squared equals to negative 1. And here's a key point. Whenever you have square minus squared, and you have a number, that's going to be a problem. Now, the only thing that you have to figure out is either whether it's this type of problem or this type of problem. It's either one of those two. Now, how do you know which one's which? Just look at the intercepts. Here, if you set z equals 0, you have these 2 points. So you must have a set of curves passing through these points. Which one is it? First one or second one?
Second one.
The second one, obviously, right? So you can just do it quickly like that, okay? Now remember that hyperbolas always have the asymptotes, just like that, okay? And because you get the same thing when you do the YZ trace, you get z squared equal to y squared minus 1. You get the same picture. So now try to picture what's going on with if the all the cross sections. See, if this is x, then y is going into the board and z is out. Okay, so so that's a three-dimensional picture. And then if you take all the cross sections, these are all circles. What is that? Okay, that's the shape. Okay, that's the shape of this thing, and this is known as hyperboloid of one sheet. Now, why one sheet? Well, that's explained if you do the same thing here. Now, this one too will have cross sections as circles, but slightly different because if you plug in 0, what do you get? You get 0 equals to x squared plus y squared plus 1, which means you have x squared plus y squared equals to negative 1. Okay. Now, what kind of circle is this? It's a circle of radius. Well, square root of negative 1 is I, right? So it doesn't exist. There is no pair of numbers that will satisfy this equation. If you have two real numbers, there's no way you can get a negative number, right? So what happens is that at z equals 0, there's nothing. Okay? Now, when you have z equals to 1, now you get something. Z equals to 1. You get 1 equals to x squared plus y squared plus 1. So 1, 1 cancels. So you get 0 equals to x squared plus y squared. That's a single point. So 1 at negative 1, you have a point. And after this, you do have a growing circle. Okay? Now, one enlightening thing that you get is if you look at the xz trace of this object that we just tried, you get z squared equals to x squared plus 1. And this time, once again, if you try to get the x-intercept, you don't get anything. However, if you plug in x equal to 0, you get two values of z. Z equals plus minus 1. So that's going to be, here's 1, here's negative 1. And we know that this is a hyperbola. So what kind of hyperbola is it? Can you draw it? Like that, right? And then all the cross sections are circles. So what does that mean? It's still called a hyperboloid because you're taking a hyperbola and you're rotating it around, right? But now it has two sheets. That's very different than that one, right? Yeah. If somebody gave you these two pictures and said these two surfaces have very similar equations, you might not believe it because they look so different, right? So this one's called hyperboloid of two sheets. And I don't have time to do this yet, but if you put 2 or 3 or some other coefficients here, that also squash things. And every time you squash it like that, then you may end up with something like elliptic hyperboloid of two sheets because the cross sections will be ellipses. Okay, so those are some additional things. Okay, so one nice thing to do after this class is to go to Wikipedia and look up what is it? 3D surfaces, okay? And it will have all these various names, and it's good to try to look at the shape and figure out what the name for that is, okay?